we will conclude this first class of our primer by taking a look at how we can pass from the Laplace transform, which, as you remember, has a complex variable that can be any complex number, to the Fourier transform, which, as you remember, has a complex variable which is on the imaginary axis. That is to say, we replace S, the Laplace transform complex variable, by j omega, where this is the imaginary unit and this is a real number, which is the imaginary part of the Fourier transform complex variable. We see that the powers of S will be replaced as follows. So suppose that we have a certain real valued function of a real variable, like this one, for instance, that we already know. And we already know its Laplace transform, which is this. To find its Fourier transform, all we have to do is to replace the powers of S according to this. Very often, however, it is convenient to separate the real and imaginary parts of the Fourier transform. As you know, we can do that easily using complex conjugates. Very often, as we will see, it is convenient to give not just the real and imaginary parts separately, but also to give the Fourier transform in trigonometric form. Remember that, given a complex number, its trigonometric form corresponds to its absolute value, that is to say, its distance to the origin and to the angle made by this straight line connecting the complex number to the origin with the positive real axis. This angle is very often represented like this. Trigonometrically, it's easy to see that this absolute value is given by the square root of the squares of the real and imaginary parts of the complex number, and that this angle is given by an arc of tangent, which is the ratio between this imaginary part and this real part. But pay attention, the arc of tangent is usually given in the range from -90 to 90 degrees, since it has a periodicity of 180 degrees. In fact, the tangent of this angle is, as you know, the same as the tangent of this angle. However, for the trigonometric form of a complex number, we need an angle given from 0 to 360 degrees, or from -180 to 180 degrees. In any case, an angle given for the whole range of values of the circle. And we can know that angle because we know both the sign of the real and the imaginary part, so we can know in which quadrant we are. This corresponds, by the way, in most programming languages to a function called a tan2. Another important thing to know about the trigonometric form of a complex number is the result of the Taylor series of the exponential. Surely you have studied this series. This means that if I want to find the exponential of a purely imaginary number, I will be faced with an expression which I can easily find applying these powers of j omega, which I have here. Now I will separate the real and imaginary parts of this series, we see that these two series are the series for the cosine and the sine. Thus, the exponential of a purely imaginary number with imaginary part omega is equal to the cosine of omega plus the imaginary unit times the sine of omega. That is why a complex number given in trigonometric form can be given as its absolute value multiplied by the cosine of its angle plus the imaginary unit times the sine of its angle, or simply as its absolute value multiplied by an exponential of a complex number with the angle here. Now that we know this, we can rewrite this Fourier transform that has this real part and this imaginary part in trigonometric form using these expressions. Notice that the imaginary part is negative and the real part is positive. This means that here in the complex plane, we will be in this quadrant here. We will have values between 0 and minus 90 degrees, or if you prefer, between 270 and 360 degrees, which is the same. This being the absolute value, or modulus, and this being the phase. When we want to pass from the Fourier transform to the Laplace transform, we have to replace in one of these expressions, preferably this one, omega by the corresponding values of s obtained inverting these expressions, and then simplify until we obtain something as simple as this.